There is a recurring phrase in our times that says, "Born too late to explore Earth, but too early to explore the cosmos." However, this doesn't mean that we should take a negative point of view. On the contrary, we should be among the first generations to mark the pioneering path towards how to navigate the cosmos. By doing so, we would be achieving the greatest leap in human history. If we want to reach Mars more routinely, we will have to learn to go and achieve much greater energies. Since after Mars, distances increase exponentially, so much so that Neptune is 20 times the distance between Mars and Earth. And once we go beyond our solar system, distances increase exponentially, and they begin to escape the comprehension of human psyche. If we want to reach other stars, we need to revolutionize our space travel systems. This system promises to double the thrust speed of current chemical propulsion rockets, cutting travel times in half. It would work as follows. A nuclear reactor would be used on board, which should be cooled with a liquid, and that liquid is precisely our fuel, meaning liquid hydrogen. The liquid hydrogen would pass through the reactor and be heated until it becomes a propulsive gas. Although there are still issues with how to manage and maintain this cryogenic liquid in space, hydrogen would be the propellant of choice due to its low molecular weight. The heavier a molecular element is, the lower the thrust or propulsion speed, essentially making the nuclear thermal propulsion system not beneficial compared to conventional rockets from today. We also have another problem, which we will present the solution to later in the video. This method might take us to planets in our solar system, such as Neptune, although it would still take about 5 years using only this propulsion method. This method remains ridiculously unfeasible for an initial mission to our second closest star, Proxima Centauri, which would take about 110,000 years. With this propulsion method alone, with a thrust of 10 to 12 km per second. If we truly want to leave our solar system, we must go much faster. This method could theoretically provide 100 times the speed of current rockets, although they currently have about 10 times the thrust of current chemical propulsion rockets. It works as follows. A noble gas is injected into an atomic ionization chamber. When the atom of this gas, usually xenon, enters the chamber, it is bombarded with electrons. When these electrons collide with the xenon atoms, the xenon atom loses an electron and becomes a cation. These electrons are then captured by a wall inside the chamber with a positive charge, while the xenon cations are attracted to the wall that will expel them, where there are two grids, the screen grid or positive grid, and a negative or acceleration grid, where the cations will be expelled at extremely high speeds, potentially up to 300 km per second in theoretical models. Now comes a major problem of ion propulsion, and that is that they do not have the necessary mass flow to accelerate a spacecraft at a fast pace. That is to say, the acceleration happens over very long periods of times, months or even years. A rocket could not be launched from Earth with ion propulsion, as it doesn't generate the required thrust to accelerate the spacecraft violently. This is the major disadvantage of this method, and exactly here, conventional chemical propulsion rockets are much better, as well as the previously mentioned thermal nuclear propulsion rockets, since they have a much higher mass flow and greater relative thrust. What these two methods lack is escape velocity, but don't worry, because we might have a solution for this method. You may have guessed it, but combining these two methods mentioned into one spacecraft would be the best we could have in the short term, as we would combine high thrust to leave Earth as well as the ability to decelerate once we reach our destination. with the huge advantage of ion propulsion efficiency, which has much higher escape velocities but much less thrust. Additionally, the onboard nuclear reactor would generate the electricity needed to power the ionization chamber and increase its power, allowing us to have more thrust and escape velocity for ion propulsion. This hybrid system could take us to the limits of our solar system in just a mere 6 months, meaning we could reach Neptune in 6 months, compared to the 12 to 18 years it would take with current technology. And that's with the gravitational assistance from a celestial body. This is a massive breakthrough. However, it would still take more than 4,000 years to reach our second closest star, Proxima Centauri, with this hybrid method. So, if we really want to get to such places, we need to go beyond what we currently have. This system could be a reality in about 100 to 200 years. Remember that 100 years ago we had just started flying, so progress happens exponentially fast. This system would use our sun as propulsion, but not literally. It would employ an onboard fusion reactor, which even today is impractical on Earth. So there are still many obstacles to obtaining it on a spacecraft. This model would employ an onboard fusion reactor, and the fusion reaction would be deuterium plus helium-3. The problem is that helium-3 is extremely scarce on Earth, tritium-2 for that matter, but there is a great solution. There is near a limitless amount of helium-3 in the atmospheres of gas giants, like Uranus, literally quadrillions of tons. So, if we mine the gases of these planets, which we will explore in a future video, we could make fusion reactors much more accessible, and thus also a fusion propulsion spacecraft. The system would work by taking deuterium and helium-3 isotopes to extreme temperatures and pressures. Then, both would collide via magnetic fields and release enormous energy when they fuse. This fusion would generate plasma, which would be guided through magnetic fields towards the exhaust, generating speeds of up to 10,000 kilometers per second and potentially more, taking us to about 5% of the speed of light in the best case scenarios. This speed would take us to Neptune in just a few pale days, making interplanetary travel in our solar system something as easy as walking a few blocks for a human, and our journey to the second closest star would be shortened from 4,000 years to just a mere century. A method that is totally realistically and achievable in this next couple centuries. This method is the only one on this list that is science fiction, but it doesn't violate any laws of modern physics. That is to say, we have huge limitations, but it is not impossible. To begin with, this spacecraft would require negative or exotic energy, which is energy that behaves very differently from conventional energy as we know of. If we could somehow cultivate this energy and use it, we could compress the time in front of the spacecraft and then elongate the space-time behind the spacecraft, and the spacecraft would remain in a kind of bubble. From here onwards, space itself would move the spacecraft would not move. This would allow for travel at speeds faster than the speed of light while still obeying relativity within the bubble. In any case, the energy we would need to make this possible would be the equivalent of a small star or planets like Jupiter, so it is still a very long way off. This spacecraft could reach Neptune in just 2 or 3 minutes, making interplanetary travel like a walk in the park for a human. An interstellar journey to Proxima Centauri would only take a few months. An intergalactic travel could potentially become a reality, maybe in a few thousand years. Just as we saw the ancient Egyptians, they will see us as the era that sparked the exploration of the cosmos.